Good afternoon, good morning, everyone out there in Cyberland. This is the distinguished lecture by Alvin Loke. That's a lecture and part of the series of distinguished talks being given here and a broadcast from the South Brazil Solid-State Circuit Society and EDS joint chapter. It's our pleasure and honor to host this talk this afternoon and morning, whatever you are. A few words about our speaker, who will be speaking about FinFET technology for you circuit designers. Alvin Loke is a technical director at the NXP. He just joined it 3 months ago at NXP. Prior, he has worked at several companies like Agilent, AMD, Qualcomm, and TSMC. He has worked over the many decades CMOS nodes spanning from 2050 to 150 nanometer down to very advanced at 2 nanometer CMOS. He holds a Master of Science and a PhD degree from Stanford University. After graduating, he spent several years in CMOS process integration. He has been an active member and active volunteer for the Solid-State Circuit Society. He's currently a member of the ADCOM committee of the society. So he's already served as a distinguished lecturer, chapter chair of 2 different chapters in Denver and San Diego, US. He is the chair of the webinar series. As you know, Solid-State Circuit Society holds a webinar worldwide promoted by the society, and Alvin is the chair of that activity. He has authored over 50 publications, served many editorial roles in several journals and conferences and program committee. He holds the CICC 2018 Best Paper Award. He is the holder of 28 USA patents. In his long career, he has many accomplishments to long to list. Thanks a lot, Alvin, for being with us. And for all of you in YouTube, you can type your questions to the speaker, and I'll read the questions at the end of his presentation for everybody to share his experience and very deep knowledge in this field. Thank you very much, Dr. Alvin, on behalf of the South Brazil section and chair, and basically in the chapter here. It's very honored to have you, and we advertise this talk all over IEEE Region 9 also. The floor is yours.
Thank you, Professor Bumpy. Hey, it's an absolute honor to be here. Thank you so much for the invitation. I hope everyone is staying safe and healthy through these trying times, and hopefully we'll be seeing each other face to face in a hopefully not so distant future now that vaccines are out. Anyways, this morning, this afternoon, this evening, wherever your time zone may be, I'm going to be going over a technology tutorial primarily focused for circuit designers. What is it that circuit designers need to know or should know in handling the advanced FinFET nodes starting in 60 nanometers. So what I'll do is, I'll start by just a brief motivation. So obviously, semiconductor demand needs no mention here. It's just exploded over the last more than half century, and largely the computing industry or different forms of computing has motivated semiconductor demand to the point where pretty much anything that uses electrical outlet or has an electrical plug has some sort of compute ability in it. So where we are now, just very recently, we finally have 5 nanometer products in the market space. Apple recently introduced their A14 and M1 processors in 5 nanometers. Now, of course, what's made all this technology advancement possible has been essentially our Moore's Law, which is essentially a simple statement in reality, an economic observation that when you make things smaller, it actually costs less. Okay, which is an incredible thing of beauty. And looking at transistor density increasing over time, giving us more and more functionality, more and more power in our devices, that's really been the heart of how our semiconductor industry has migrated along the last half century. So through the course of scaling, we can kind of break it down into 3 eras. The first, lasting over 3 decades, is the time of Dennard scaling, which has taken us down to about 130 nanometers. Beyond that, we needed to enter a new era where mechanical strain and HighK gate dielectric and metal gate were introduced. This is the time of sometimes referred to as equivalent scaling. This brought us down a few more nodes, and starting in 22 nanometers was the time when the FinFET device architecture was introduced, and this was also the time where extensive design technology co-optimization was necessary to continue this cadence of scaling. So just a quick outline of how we will proceed this morning. First thing I will cover is kind of a walk through memory lane, go through an evolution of how we arrived at the FinFET. We'll then cover the technology scaling enablers that has made these advanced nodes possible. Talk about the consequences of these new technologies, as well as some design strategies to handle the technology. I'll then take a quick peek into what's further ahead in terms of how FinFETs are continued to be optimized, as well as a look at gate-all-around structures, and finally conclude. So looking at how FinFETs have evolved, we'll cover Dennard scaling, extended Dennard scaling, and then start going into fully depleted devices. So any talk about transistor scaling will need to mention the whole thing about short channel effects. Okay, so basically what happens is as you scale the contacted gate pitch between basically the spacing between the transistors, essentially, that necessitates area scaling necessitates reducing the contacted gate pitch, which in turn necessitates reducing the gate length. Now, of course, this doesn't happen for free because when you try to scale the channel length, you start to get short channel effects. And this is simply because you've got source and drain to body depletion regions, which nature basically depletes for you for free. The action of the gate to try to basically deplete the footprint underneath the shadow of the gate is already having part of its depletion region depleted by the source and drain junctions. And this essentially weakens the gate control, which in turn causes threshold voltage roll-off. The other manifestation of short channel effect happens when you increase the drain voltage. And as the drain voltage increases, the depletion region thickens on the drain side, which further reduces the control of the depletion charge by the gate, causing what's referred to as drain-induced barrier lowering, or Dibble, which is basically a manifestation of the VT getting reduced as you increase drain voltage. So the scaling recipe that's been used to deal with short channel effects is the long celebrated set of guidelines provided by Bob Dennard in his seminal paper in the early 70s, where basically if you try to scale a transistor by, say, a factor of alpha, and you try to reduce the gate length, there are several other things that need to scale in addition to gate length. So notably, as you scale the gate length, obviously the depletion regions associated with the source and drain to body junctions need to get thinner, and that necessitates the body doping to increase. Unfortunately, increasing the body doping causes the threshold voltage to increase, which necessitates the oxide thickness to go down to recover some of the gate coupling and reduce your threshold voltage. And since we are now having thinner gate dielectrics, that requires the supply voltage to also scale down to make sure that you don't have issues with dielectric breakdown. So this has been essentially the recipe, the blueprint for our industry for about 3 decades. It spanned from 10 microns to 130 nanometer microns, where we had essentially 2 orders of magnitude reduction in gate length as well as oxide thickness. Now, along the way, we've had to introduce several innovations to extend the short channel control. One is extensive body doping profile optimization, where the body doping in both the lateral as well as the vertical direction has been highly tailored, made non-uniform as a result. The halo implants were introduced underneath the edge of the gate to basically increase the doping concentration there to reduce the depletion region thicknesses and therefore get you better short channel control. Okay. Also, in conjunction with that is the formation of these spacers to enable these short channel, or sorry, very short source drain extensions, very thin source drain extensions to allow the depletion regions to contour away from underneath the shadow of the gate to get you better short channel control. Okay. Now, there's been several obstacles to continue Dennard scaling, and as we mentioned, the way to deal with having thinner and thinner depletion regions is to have higher body doping. And one of the consequences of having higher body doping is more ionized impurity scattering, which causes your channel mobility to degrade and therefore your current to degrade. Furthermore, as we're thinning the gate dielectric, we've been experiencing severe direct gate tunneling leakage through the nitrided oxide that historically has been used. And further that, with the polysilicon gate not being a very, very good conductor, we actually end up with gate depletion in the polysilicon gate, which moves charge away, and also quantum confinement due to the high doping concentration, where you've got essentially limitations in density of states. The net effect of all this is that your charge on the gate and is being mirrored by charge in the body that's spaced apart further, which effectively reduces your electrical separation between charge and therefore reduces your oxide capacitance. So the two innovations that has enabled Dennard scaling, continue to enable extend Dennard scaling, has been mechanical channel strain, as well as the use of HighK gate dielectrics and metal gate. So let's talk a little bit about mechanical strain. So mechanical strain is largely a trick you play to improve the mobility of the transistor. We're exploiting the fact that silicon is piezoresistive, which means that basically its electrical properties depend on its mechanical strain state. And this is quite amazing, because a material like silicon, if you can somehow introduce 1% of channel strain, that can actually reduce the carrier effective mass of electrons and holes several times, such that you can actually increase the mobility several times. Okay. Now, because of the high Young's modulus associated with silicon, this means that to achieve this kind of channel strain, you need to surround the transistor with stressors, mechanical stressors that are in the order of several gigapascals. Just as a reference, this is actually several times the yield strength of high strength carbon steel. So the beauty of this, of course, is you can increase the on current for the same off current without increasing the oxide capacitance. Now, as noted here from the cartoons below, the NMOS and PMOS transistors, they want opposite stress along the channel length, but the desired stress is actually quite complicated and depends on direction, therefore anisotropic. With that said, mechanical strain techniques only work well for short channel transistors. They're not effective for long channel transistors, because as you can imagine, you have these stressors that are trying to impart stress on the channel in between. As the channel length gets longer, the volume of silicon surrounded by the gate is increased, therefore more effective at resisting the pressures coming from the surrounding source of drain. There are a host of different techniques for introducing mechanical strain. The most notable one in FinFET node is actually the use of silicon germanium source drain stressors. So looking at the other key innovation that has extended Dennard scaling is HighK metal gate and gate dielectric. So here we are trying to basically extend to some extent the oxide capacitance without the severity of gate tunneling leakage that we're experiencing. So what the industry has migrated towards is a HighK material that consists of essentially a hafnium oxide based dielectric. And by making the hafnium dielectric thicker, and because of its higher dielectric constant, you can still preserve your COX. That thicker dielectric essentially gives you is effective at suppressing gate leakage. Now, HighK dielectric has to be coupled with a gate material that consists of essentially a conductive work function metal layer that sets the work function and therefore the flat band voltage and threshold voltage of the transistor. Because typically the work function metal is very resistive, you typically need to have a very thin work function metal and fill the rest with a much more conductive metal fill material. And the combination of this basically gives you a much less resistive gate material, which results in less gate depletion. Now, because we are replacing both N+ and P+ poly gates in a planar process, a non-HighK metal gate process, you do need a different work function metal to achieve that for both NMOS and PMOS, because you essentially need to have work functions that line up with the conduction band edge and valence band edge of silicon. Okay. In these technologies where it was introduced, starting in 45 nanometers, to get the multiple VTs, we still, despite having multiple work function metals, required using body doping and implants to essentially tune get the different flavors of VT. Now, there are lots of integration challenges associated with this technology. For one of the key problems with HighK metal gate is that the metal gate to the HighK interface is thermally unstable, which means that subjected to the high temperature source strain anneal that's typically used to activate dopants, you can get significant shifts in VT that essentially renders your transistors non-functional. And so the industry solved this problem by migrating to a replacement metal gate process, where essentially you would build your gates using polysilicon until the very back end, do the source strain anneals first, and then after the source strain anneal and subsequent contact dielectric deposition and back polish down to expose the top of the gate, you rip out the polysilicon gate, and in a Damascene atomic layer deposition process, you basically deposit your HighK dielectric and the various layers of your metal gate, and then subsequently polish away to inlay the metal gate. Okay. Another integration challenge associated with HighK metal gate is the resequencing of the silicide module. One of the requirements of a HighK dielectric is that it undergoes a post-deposition anneal for gate oxide reliability. And in order to do that, it inadvertently will essentially destroy the resistivity, the low resistivity of the silicide you use. So what that means is you have to postpone the silicide module until after the HighK deposition step. So even despite the advent of mechanical strain and HighK metal gate, eventually we reached yet another roadblock, and Dennard scaling essentially came to an end. We need to understand why it came to an end. We need to basically understand, well, what is going on with the transistor in subthreshold. So a transistor, a MOSFET transistor in subthreshold is essentially a bipolar junction transistor, where the base is essentially the surface potential node that's not directly coupled to an electrical node such as the base, but it's actually controlled by capacitive coupling between the gate, controlling it through COX, fighting against basically parasitic capacitive coupling due to the body and drain. The problem is that as we are scaling, mandating higher body doping to suppress short channel effects, we are actually making the depletion regions thinner and thinner, which is good for short channel control, but in turn increases the body and the drain coupling. Okay, and the net result of this is that you have higher subthreshold swings. Okay, in terms of how many millivolts of a gate voltage change you need to affect 1 decade of subthreshold current change, and that is obviously incongruent with your supply voltage and your threshold voltage scaling for lower power. And so what that means is, if you're going to keep scaling the channel length and still have transistors with performance, because of this subthreshold swing limitation, you end up getting very high leakage. So what the industry has done is to pay much more close attention to the use of fully depleted structures to achieve, to overcome some of this limitation I previously mentioned. Now, before we do that, to motivate what a fully depleted device is, it's important to realize that, well, how does a field effect transistor actually work very simply, when you apply gate charge, that essentially sets up in the form of the ionized dopants that are in the body, essentially mirror charge in the form of fixed acceptor charge in the case of NMOS. And that sets up a dipole, which in turn sets up electric fields, which then integrate to get you surface inversion. And that surface inversion then allows a conductive channel to form. Now, one thing that's key and fundamental in understanding fully depleted devices is that surface dopants are not fundamental to field effect action. In fact, if you can actually push these dopants further down, okay, leaving behind a region of undoped surface here, you could, in fact, very much build a field effect transistor. And this actually has a bunch of advantages. Number one, because you have, in principle, no dopants in this fully depleted layer here, you basically have much less channel scattering because you don't have the ionized dopant impurity scattering, which causes your mobility to go back up. Okay, you also don't have field lines in the absence of charge here to terminate fields that come from drain charge. You don't have as much field lines terminating in from the drain terminating here, which means that your Dibble is reduced. And basically, the structure, what we are essentially doing is migrating from a geometry-based or a dopant-based structure to a much more geometry-based structure where we essentially have built like a parallel plate capacitor device. Okay. Now, there are multiple implementations of a fully depleted device. You can build a planar on bulk, although this is very difficult to do because growing an epitaxial layer of undoped surface requires high temperature, which results in a lot of outdoping from the heavily doped region underneath. You can do planar on SOI, where basically this region here can be replaced by an SOI layer and a barium oxide layer underneath. You can also have 3D on bulk, which is what we know as FinFET, or 3D on SOI. So what is the beauty of having a fully depleted device? Well, when you have a fully depleted device, basically you have substantially less body coupling and drain coupling, which means that your subthreshold swing is a lot steeper. Your Dibble is going to be a lot better, much more reduced, and your body effect is essentially near non-existent. Okay, and by being able to reduce the threshold voltage, if you preserve the same overdrive for the same performance, essentially what you can do is you can bring the supply voltage and the threshold voltages down while still preserving the same off and on current, which is a thing of beauty, obviously. Okay, and just to kind of put some numbers to this at room temperature, in the last planar nodes, we were seeing subthreshold swings as high as about 120 millivolts per decade. So if you hypothetically say you need 3 orders of magnitude separation or 1000x difference between on and off current, that requires a minimum threshold voltage of 3 decades times 120 millivolts per decade, or a threshold voltage minimum of 360 millivolts. If you can somehow bring this down to a much lower subthreshold swing, such as in a FinFET, the first FinFET nodes came down, brought the subthreshold swing as low as, say, 65 millivolts per decade. Multiply that by 3 gives you 195 millivolts, which means that just by going to a FinFET, keeping the overdrives the same, you effectively can bring the supply voltage down by about 360 to minus 195, or about 165 millivolts reduction in threshold voltage. So this is a very big deal. Okay, now Dibble typically is referred, is manifested in the form of a poor output resistance in a transistor, as you can see here in a plot of drain current versus drain voltage. But less Dibble, and this is perhaps a little bit less intuitive, is actually better not just for analog circuits where you want high R out, but also for digital circuits. So if you look, for instance, at an inverter, and you make that inverter switch from an output of high to an output low, look at the inverter switching trajectory of the NMOS transistor, you can see that basically the inverter, the IV characteristics of the switching device goes through this path. And if you were to use CV over I as an estimate of the switching delay, you can see that the historically used ID SAT is not a very good estimate of the average current during this trajectory. So IBM had introduced in the early 2000s this concept of this effective current, which is basically the average of a low and a high current as defined here. And this results in the I effective, which is actually a much, much better estimate of switching delay if you were to use a CV over I estimate. Now, the beauty is that if you go to the device that has much, much less Dibble, the intuition here is that your high current is higher, which in turn makes your effective current higher. And this can actually, by having a device which not necessarily has a higher ID sat, just has the same ID sat, if you can preserve the Dibble or make the Dibble much, much less or eliminate it, you can actually get a transistor that can have much faster digital switching, quite often well over 10% improvement. So with that said, as a background, I'd like to now turn to technology scaling enablers and talk about the FinFET device and lithography, more stressors and HighK metal gate, as well as middle end of line, self-line contacts, and other DTCO innovations. So looking at a planar transistor and migrating to FinFET, basically what you're doing is you're so-called finifying the active region. For every fin pitch, you're basically creating a fin out of it. And you can think of it as tectonic plates that smash into each other and creating mountain ranges out of it, where you've got, say, a gate on top of it, basically going along for the ride as the mountain range goes up. Okay. Some properties of the fully depleted fin. As we are doing this, one of the key advantages of going into the third dimension is that the device width per fin, which is basically twice the height of the fin plus one width of the fin, is quite substantial compared to the fin pitch. In fact, actually, the effective width is about 3 to 4 times the fin pitch, which means that you're getting a lot more on current and therefore more GM per unit area. Now, because each fin has a quantized device width, this does pose some challenges for SRAM, and so the industry has migrated a host of assist techniques, such as read and write assist techniques, to get the cell readability and writability using variable voltages to kind of fine-tune the granularity that you lose by having integer number of fins. For logic is also a little bit of a problem. It's not as big of an issue for analog circuits because the supply voltages are, the overdrives are actually quite low, and you're not getting a lot of GM per fin. Typically, no more than in the order of 10 to 100 microsiemens per fin. And when you're working with millisiemens kind of GMs, you obviously need multiple fins at the minimum to achieve. We talked about less Dibble for higher R out and better intrinsic gain as a result. The body effect is essentially negligible, with typically less than 10 millivolts of VT shift across a supply voltage change in body to source biasing. The mismatch is substantially less in such a device because in a fully depleted device, in principle, you're not sensitive to random dopant fluctuation. However, you are still seeing that variation does depend on area and geometry, as well as orientation of the HighK metal or the metal gate grains. This all comes at a price, though, of increased parasitics. There's substantially more parasitic given a much more compact three-dimensional structure, with nodes being much closer to each other. The source drain resistance is much worse because of spreading resistance to get into the fins, as well as the coupling to the gate. Because the fin width is much less than the fin pitch, the junction capacitances are, although they're low, which is not really a significant factor because the parasitics are dominated elsewhere, but you have much higher well resistance, which has latch-up implications. And lastly, 1 over F noise is going to be comparable to much worse. And lastly, because we're just moving more current in a smaller area, the self-heating density is a concern, which raises reliability concerns. So a quick dashboard that was very nicely summarized by Lawrence Lowe in an ISSCC short course several years back. Basically, the benefits of going from a planar node like 28 to 16 and 7, which are FinFET nodes, you can see that the supply voltages have come down, which has obviously resulted as a result of the VT going down due to the steeper subthreshold swings. Leakage has been substantially reduced. On resistance has improved, GM has improved slightly because of the area benefit, just the more GM per area, as well as higher mobility, and the R out has obviously been better, and the mismatch has also been reduced. So you can achieve all this in lower area. So generally a very good power performance area story if you're using only FETs. One thing to note though is that analog circuits don't use just FETs. The other side of the story is not quite so positive, but if you're using transistors only, which is largely for SRAMs, logic, using FinFETs is great. Now keep in mind that the scaling benefits do saturate after the first migration to a FinFET because the device architecture has largely been evolutionary as we have gone from one FinFET generation to another. Of course, no talk about transistor scaling is incomplete without a mention of geometries scaling. You can see here a plot here of minimum pitch of the gate metal and the fin pitch, okay, as a function of time. And one of the first things you'll note is that the physical scaling rate of actual dimensions in an IC is actually slower and slower, getting more and more incremental compared to the historical 0.7x every 2 years. Okay, so what that means is even though we continue to scale the node name by this factor, it means that the node name is really more of a marketing moniker more than anything else. It's not really tied to L gate, but it is tied largely to area scaling because we are coming up with other tricks not associated with direct feature size reduction in order to achieve area scaling. So extreme ultraviolet did get introduced at 7 nanometers, but partway through 7 nanometers. In the meantime, you can see here that with the lithography limited of a single exposure limited to 876 nanometers for 193 nanometer immersion lithography, with a lot of points here beneath that threshold, you can see that to achieve all these sub 76 nanometer pitch without extreme ultraviolet, first off, it's possible, but it's come with process complexity and cost. So what are some of these innovations? The first notable one is pitch splitting. So here you have very fine pitch you cannot print in one mask. And so you basically interleave 2 or more exposures that you can print with one mask. This works, but has a fundamental limitation that there is misalignment or overlay tolerance between the masks that will limit, for instance, in this case here, how much you can push this technology. Another approach is to use orthogonal cuts, which was introduced by Intel in 45 nanometer node to reduce SRAM area. The idea here is that you print horizontal lines first and then use a cut mask to basically break the features. Why is this important? Because if you were to just print a line with a wavelength limited exposure, you end up with all sorts of essential near field diffraction artifacts, rounding at the ends, and also line pullback. By doing this cut pattern technique, because the cuts, the ends of the cuts, any non-idealities are outside what you're trying to cut, you really don't care about those artifacts. And so this allows you to reduce your end-to-end spacing between features, giving you much sharper features, and just compacting everything a lot more. The downside of those, of course, of this is it's limited by mask cut overlay in the Y direction. So with overlay or misalignment being a theme here, obviously there's been a lot of motivation to look for self-aligned patterning approaches that are more insensitive to misalignment or overlay errors. So SelfSpacer based patterning is the key trick that's been used. It's sometimes called sidewall image transfer. What you do here is you basically, the goal here is to pattern a sea of spacers with a single feature width. And the idea is that we're using this technique actually to pattern fins, short channel gates, middle end of line, as well as lower back end of line patterns. So you start by patterning with a single exposure, a sacrificial mandrel, and you use this mandrel to basically grow or deposit and etch, grow spacers on the sidewall here. You now have 2 spacers for every mandrel, which means that after you remove the mandrel, you're left behind with twice as many spacers at half the pitch of your original mandrel. Okay, and then you can use this pattern essentially as a hard mask to pattern your features underneath. Now, this here is limited to a pitch, a spacer pitch of half of that of the mandrel, or half of 76 nanometers or 38 nanometers. If you need to push further than 38 nanometers of a feature, you basically repeat this madness one more time, where you use spacer 1 as your mandrel for growing a set of spacer 2s, leaving behind twice as many spacer 2s as spacer 1, or 4 times as many spacer 2s as mandrels. And this technique here can bring us down theoretically to 1/4 of 76 nanometers or 19 nanometers in feature pitch. Okay, and so this is referred to as self-line quadrature patterning. Now, one of the benefits of these techniques is that because the spacer that's deposited is a conformal process, the line edge roughness of things that are patterned using these features, these spacers, is going to be a lot less, leading to less width variation compared to if you were to use photoresist to pattern something where the line edge roughness on the left and the right edge are not correlated, leading to more width variation. Okay, there are spacers variations you can apply to spacer-based patterning. One is to use a spacer trim mask to basically trim some spacers to a different feature, such that you can accommodate, for instance, 2 different channel lengths. Another thing you can also do is to use these techniques in conjunction with a block mask, where you're using photoresist, essentially the bridge between 2 or more spacers, to basically get you more flexibility in features, feature dimensions. Okay, so let's now get to extreme ultraviolet. So as I mentioned earlier, ultraviolet was introduced into production by the foundries at 7 nanometers. Of course, with any lithography tooling or any lithography platform change, typical problems we face are having a source power that is high enough so that you can expose these wafers typically in a reasonable amount of time for a good throughput, as well as resists that can maximize the exposure effectiveness of every photon that it gets. Okay, one thing that's characteristic of EUV is because 13.5 nanometers is such a short wavelength at which essentially nothing is refractive at those wavelengths. Everything is reflective or absorptive. Basically, EUV tool platform is all based on reflective optics instead of refractive optics. Okay. With that said, one of the beauties of using EUV, and this is what was done more so by TSMC, is really for process simplicity and cost reduction. So if you are to try to pattern very, very fine features, typically it's not uncommon to have as many as 5 masks, 193 immersion masks, with a combination of several pitch split line masks, even the cut masks or pitch split and block masks. You can reduce all that to a single EUV mask, and that basically gives you, it's a simpler process, fewer defects. All in all, you get essentially better cycle time and cost savings. And you can see going from 5 EUV masks, you can see features here, much sharper lines because you're cutting the mask, where if you had a single EUV mask, you have more corner rounding, but you can do this all with 1 mask. Okay, so going to mechanical stressors in FinFET, it's the same basic idea, but a lot more complex, okay? Because in a FinFET, we have a protrusion of the device in the 3rd dimension, which means that the sidewall of the fin has a different crystalline normal orientation compared to the top of the fin, okay? And the options due to integration constraints are much fewer for incorporating mechanical stress. And because we're continuing to aggressively scale down the gate pitch, it's making it less and less the stressors are becoming more and more difficult to incorporate because you have less volume of stressors to basically squeeze or expand the channel in between. With all these things said, the result is that these techniques are much more effective for PMOS than they are for NMOS, meaning that the beta ratios or relative strengths of NMOS relative to PMOS has been approaching unity. Other things to also note is that the stress does depend on all sorts of different factors, such as the diffusion, active area length, width, space, as well as source drain volume. And so the long story short is that when you have mechanical stressors, you're having much more severe and significant layout dependent effects, which gives rise to more simulation gaps between pre and post layout. Okay, moving along, FinFETs in HighK metal gate. We are, basically doing the same thing, extending HighK metal gate into the FinFET node. Because we have a much shorter channel length and a much smaller volume of fin wrapped around and severe RDF, the doping the transistor body to or the fin to get VT adjustments is no longer feasible beyond 14 nanometers. And so we're largely using metal gate composition as well as the HighK dipoles to achieve VT adjustments. The metal gate layers are very resistive, which means that the charge in your gate is not all contained in the metal gate layer. In other words, your Debye length is of your gate charge is essentially thicker than the metal gate layer itself, which means that some of it spills into the metal fill, meaning that the effective gate work function is influenced also by the metal fill material as well as its thickness. And just want to just reiterate that we're having substantially more significant gate resistance as well as source drain resistance with the silicide blast integration. So I just want to just quickly throw in a refresher on what flat band voltage is. So the flat band voltage is basically the so-called offset voltage, which dictates what the threshold voltage is. The threshold voltage is basically flat band plus the changing gate voltage required to transition from flat band to inversion. Okay. Now to achieve this offset, basically we look at the terms that impact the flat band voltage. Consists typically of three terms: a work function difference, a fixed oxide charge at the silicon surface interface, as well as trapped charge or fixed charge in the dielectric. So the way we are actually adjusting the VTs are through either work function adjustments or through the introduction of the so-called dipoles that we drive into the dielectric to basically adjust the threshold voltage or flat band voltage, which in turn adjusts the threshold voltage. The middle end of line is way more complex than these nodes. It's very difficult to land diffusion contacts and gate contacts. This is typically where all the yield problems are in a fab. Historically, in 28 nanometers, we had a single mask to do this. Well, guess what? As we've gone on to these more advanced nodes, we've had to incorporate the use of gate dielectric caps on top of the gate, such that when you have these self-aligned contacts that are misaligned, we don't short the contacts to the gate. Furthermore, we may need to put dielectric caps on top of the contacts, diffusion contacts, which in turn allows us to do self-aligned source drain as well as gate contacts without shorting to the other nodes. Long story short, this is a much more complex middle end of line, which is the contact modules. Accessing the transistor from the metallization above requires many more interfaces from vias and contacts, which in turn increases the FET access resistance. Just a quick look at self-line gate contacts here. So self-line gate contacts is a new feature that was introduced by TSMC in 5 nanometer. The idea here is that we no longer need to land the gate contact on the gate overhangs. We can actually land the gate directly, gate contact directly on top of the gate, on top of the diffusion. And so this allows us to reduce the standard cell height and therefore reduce the overall area of a standard cell. And also benefits reducing non-quasi-static effects because you have less effective gate resistance. The gate cut last is also another DTCO trick that's used. The idea here is that typically we would cut our poly way in the front end, which then when we use the replacement metal gate integration requires that you have sidewall HighK metal gate deposition. Well, having this increases the gate overhang between, say, an NMOS and PMOS in a standard cell. But if you, for instance, were to essentially keep the gate cut until much later, where you basically deposit the HighK metal gate module first, and then you just cut and break the gate in one step, that allows you to reduce the overhang outside of the fins, allowing you to reduce the fin-to-fin spacing, which in turn reduces your standard cell height and standard cell area once again. Okay. Another DTCO trick that's used is using double diffusion or single diffusion breaks. So the idea here is that if you have a much more, without conventionally, what you typically need to do is to have dummy gates to terminate FinFETs. Okay. And this typically incurs a lot of dummy gate waste and can increase logic area by quite a bit. If you can have a more aggressive isolation process and basically have a shared dummy gate for both left and right devices such that they can butt to each other, you can save 10 to 20% logic area. Once again, not related to reducing feature sizes, but doing everything else outside in order to get your area down. Another key thing that's important in these new nodes is DTCO trick is the use of fin depopulation. So the idea is that if you use fewer fins for both your NMOS and your PMOS, okay, and here we have the same number of fins for both N and P simply because the beta ratios are essentially unity. You can see here that as we migrate from a 4-fin cell, say, to a 2-fin standard cell, looking at the power versus efficiency, you can see that, well, you're not really, reducing the maximum frequency by very much, going from 4-fin to 2-fin, but then the power efficiency of going to a 2-fin is substantially less, or substantially better. And so this process actually favors using fewer fins in order to get the most efficient performance for a given power. So let's now move on to some design realities resulting from all these technology updates. So the first thing I want to talk about is just the ubiquitous use of stacking FETs. So as you can imagine, with the replacement metal gate process being requiring some sort of a chemical mechanical polishing step, which typically has dishing issues, it imposes constraints on what the maximum gate length can be. And so what's been very, very common is to basically stack a lot of short channel transistors in order to achieve an equivalent long channel length. Okay, this is a much more process-friendly thing to do than using longer channel length, because short channel logic gate devices are the priority for the foundry. There's also another key benefit here. Because we have short channel transistors, they benefit most from mechanical strain boost. And therefore, you could, in principle, even have need less area using stacked devices, despite the overhead of all the intermediate diffusions, because you might be needing fewer fingers to achieve a certain transistor device GM. Now, there are some side drawbacks to that. One drawback, of course, is that these intermediate diffusions are basically capacitive AC shorts at high frequencies, which means that things like, for instance, your output resistance as it relates to gain, common mode rejection ratio, things like that do get degraded at higher frequency. So you can see here, if you were to use a stack of L-min devices versus a long channel device, you can see that the R out actually rolls off at a lower frequency. Thick oxide I/O devices continue to be used. Basically, these advanced ICs, even though we scale down the supply voltages even lower and lower towards like roughly 3/4 of a volt, you can see here that general purpose IOs that typically have signal swings of 1.8 volts continue to be used, because these advanced IC node chips need to talk with cheaper peripheral ICs that are made in cheaper nodes. It is a challenge to keep these I/O devices for a host of different reasons. The main one from a technology perspective is, as you scale the fin pitch down lower and lower, your replacement metal gate process has a much more challenging time to deposit a thicker dielectric, which is shown here as your gray HighK dielectric, sorry, your blue, light blue, and gray would be the dielectric you need to deposit for a thicker oxide IO FET. It is tougher to build level shifters also in this process because you need to bridge a larger supply voltage difference. This problem will continue to get worse and worse as we move towards nanosheets. With that said, you can solve this problem from a system perspective, repartitioning the IOs, trying to encourage the use of much lower IO swing communication, so forth. Let's briefly talk about passives. So thin film resistors are now used. Poly resistors are no longer available in these advanced nodes, largely because of the HighK metal gate integration. They typically live in the middle end of line or in the lower back end of line. The problem with resistors is they are, you can use metal gate resistors, which are smaller, but they have much higher variation. Inductors remain pretty much unchanged because they use the uppermost back end of line layers that are needed to be thick for supply current distribution. Capacitors, we basically see some capacitance density improvement with back end of line scaling. However, we have to pay attention to the fact that the metal space now has gotten so tight that we can be limited by reliability constraints. And lastly, in some process steps, some process technologies, you can have a planar metal insulator metal technology capacitor way up for supply noise reduction. Okay. Lastly, looking at diodes and bipolars, for instance, that are used in ESD, band gap references, thermal sensors, things like that. As I mentioned earlier, well excess resistance is a lot worse, which means that series resistance is going to be a bigger problem, which gives rise to things like stricter well tie rules, latch up, guard rings. All these things are just more painful. Long story short, passives are having either no scaling or very limited node-to-node scaling. And so as the process cost goes up per square millimeter, it's going to be increasingly expensive to incorporate these traditional analog elements. Interconnect resistance is a big deal. One could argue that in an interview, so long as you mention that resistance is the most painful thing you have to deal with when you're building or doing circuit design in FinFET, you have the inside. No. The problem with interconnects, for instance, is that copper barriers are not scaling. That in conjunction with scattering effects means that the resistance of the most compact or most highly dense lines are actually soaring very quickly as you're going from node to node. And that's something to grapple with. So what that means is that the FET performance is going to be very significantly compromised by source degeneration. And in these nodes, it's all about preserving every last millivolt of the source side IR drop to minimize a performance loss from reduced overdrive. Gate resistance is also a problem, it has very complicated horizontal and vertical components, as you can see here. You can mitigate this generally by using fewer fins, double-siding your gate contacts, and if your process enables this, Selfline gate contacts. Gate-to-contact capacitance is a big deal because you've got basically essentially Selfline contacts and your epi and your source drain essentially in very close proximity to your gate, leading to very high vertical parallel plate capacitances, which gives rise to all sorts of circuit issues where Miller coupling, for instance, or even source side coupling can be an issue. And these are just some examples where noise can actually degrade your performance of your circuits. I talked about flicker noise briefly. Flicker noise is at par to much worse in a FinFET node. So flicker noise obviously is a strong function of interface quality, because it's a trapping and detrapping phenomenon that dictates it. So you've got all sorts of different factors. You know, you've got the HighK dielectric, you've got channel orientation with a different normal. Long story short, it is a nuisance to deal with flicker noise. And what makes it worse is that as we are starved with headroom, the flicker noise is actually a lot worse at lower gate overdrive. But having said all that, it is not a showstopper. Typically, you can overcome it with basically more area to reduce the flicker noise, or go to more exotic circuit topologies. I want to allude now to some basic stress layout dependent effects. So as I mentioned, these transistors are heavily strained for mobility enhancement, which means that when you've got differences in mobility in the surrounding regions, it's going to relax or enhance the stress of the transistors. And so, you know, you've got the basic layout dependent effects. And as I mentioned earlier, you get a more and more simulation gaps between your pre and post layout. The models do capture this, though. Okay, now one layout dependent effect that's worth mentioning is the gate cut stress effect. And so the idea here is that if you have gate cuts, okay, very near a transistor where the gate is not cut, it turns out that actually these gate cut stresses can modulate the stress fields around the transistor and therefore impact the behavior of the transistor here. So you can see here that by having the gate cuts nearby, that actually can modulate your transistor stress. Thankfully, it is captured in our models. We've got layout dependent effects for the HighK metal gate process, where, you know, when you've got different work function metals in the same gate, unfortunately, you can have interdiffusion of work function metals, which in turn causes variation in VT when you've got one, for instance, a transistor very near a work function of a neighbor transistor. Okay. Density gradient effects, also related to layout dependent HighK metal gate, is another big concern, where when you have gate density gradients causing metal dishing, as I mentioned earlier, the work function of the transistor is effectively impacted by the height of the metal fill as well as the metal fill metal itself. It is very difficult to capture, and so that's something to pay attention to. Now, leading to now how we put all this together in these advanced nodes, density is a really, really big concern. Typically, all the critical process steps are very sensitive to pattern density and a process loading. We've got thousands of DRC rules, very difficult to pass if you're not careful, and they're very difficult to even understand what they even say or mean. There are lots of all sorts of unmodeled effects that needs to be contained by having stricter DRC rules. We have all sorts of different densities. We look at area, not just area, but also perimeter and gradients. And so this is an example, for instance, of a digital PLL floor plan. You can see here that the floor plan is a little bit more tedious and bloated. We've got lots more dummy gates, belt taps, things like that, guard rings. And if you're not careful, you might actually need to insert wasteful transition regions to basically grade the density from regions of, say, high gate density to regions of low gate density. A little bit about process loading related variation. So here, these are some examples of things that are very difficult to capture in the models, but do exist. So for instance, deposition loading. As I mentioned earlier, we are using spacer-based patterning. And so if, for instance, you've got, say, a region where you've got very high density of features versus low density features, you can see that the spacers that are deposited, for instance, could have a different width, which means that your critical dimension, your feature sizes, will be impacted by this loading effect. Epitaxy loading is yet another factor where, you know, you could get different types of epi growth as a result of having different density. And also, you could have etch loading effects as well. Okay. There are long-range density-related factors as well, where, for instance, rapid thermal anneal, if you're not careful with your active density and your gate density, you can actually change your surface absorptivity enough, make them non-uniform enough such that the temperature variation in your rapid thermal anneal will give rise to a lot of device variation. And lastly, of course, CMP, chemic polishing. There are lots of different electrical impacts of having a long-range density variation. Just a quick commentary about the FinFET node models. These models that we use are now exclusively BSIM CMG, which is based on surface channel surface potential. It's less equation fitting. But our models for the latest nodes are target-based and speculative, and there is more and more silicon influence in the more mature nodes, but it is prone to a lot of things that are not being modeled. The back-end models typically very little, only electrical information is provided. Very little physical stack-up details are now available, largely for the foundries to protect their IP from getting into the hands of competitors. One thing I did want to say is that along those lines, the foundries are extremely paranoid to not share anything. Share enough such that you can do your design, but not more. For instance, things like the process corner methodologies and many of the model parameters are encrypted. There's very little physical information available in terms of physical details. So for instance, basic dimensions like gate length are not even real. A quick word about doing bleeding edge product development. You can see here that these designs, the very most advanced nodes are done with the technology and design done concurrently to shorten the time to market for products such as the 814 released recently by Apple. So what that means is the models we get initially are target-based or projections. Okay, and basically what happens is over time, the fab basically has more confidence in what they can achieve, but they will likely produce a new set of models or DRC, which then we use for updating our design and iteratively do this in hopes of basically having an earlier design finish. Okay, and one last thing to also highlight here is that in light of all this, the technology and the modeling is highly prioritized to the logic and the SRAM FETs, not so much analog application. Just a few things to note about the pre and post layout gaps that I've alluded to. You just need to accept the fact that you're going to need more and more iterations to close on your design between a schematic and layout. It's never too early to start your layout. There are a bunch of different sources of deltas for the gaps, the layout dependent effects, as well as the middle end of line and back end of line parasitics that are not anticipated in the schematics. There are things that are estimated in the pre-layout netlist, which helps. For instance, the source drain resistance, gate resistance, as well as the gate contact capacitance, but you can't capture everything. Okay, and so if you can back annotate layout dependent effects and parasitics into the schematic using more a tile-based, template-based approach of layout, you can speed up the productivity of your design. Okay, so what I want to allude to now is some of the design strategies to achieve, to deal with these advanced nodes. And so one that takes a little used to is to avoid mixing, for instance, short and long channel transistors. Okay, so for instance, we know that the short channel transistors are patterned using spacer-based patterning or Selfline double patterning, while the long gate transistors are patterned using conventional mask. And so the problem is, if you want good process control of that, it's very difficult to build something, for instance, like this, where you've got long channel, for instance, long channel transistors used as a current mirror, and typically short channel transistors used for enabling or disabling this current mirror. One approach to fix this problem is, making everything long channel, like you see in this approach. But then a more preferred approach is if you can somehow stack, make the long channel devices out of stack devices. This is a more process friendly because you are using more and more short channel devices. Okay, I talked about resistance being a real challenge, especially for high current circuits such as I/O drivers and clock buffers. So these are just a couple of examples of how you can mitigate the resistance. One is to use a double source layout where you basically insert a dummy diffusion a dummy gate in between to be able to land another source drain contact, such that you basically have the current flowing through each contact, and therefore having the ohmic drop across that contact. Okay. Another one is landing vias. If you can somehow make your source drain extension, or your self-line contact, your diffusion contact longer, so that you can land an extra contact. This may not seem like a big deal, but this, for instance, is a very valuable trick to actually reduce your overall ohmic drop in accessing the transistors. Okay. Via pillars or layer promotion can be a very valuable trick to reduce resistance. So as I mentioned earlier, because the middle end of line metallization is so resistive, if you have long routes, okay, it might actually be better for you to layer promote to a much more conductive metal layer at the top. In the process of doing this, you do eat the burden of having more series resistance in via resistances getting up and down. However, if you, for instance, were to create these via pillars to reduce your via connectivity resistance, you can actually end up with a much lower overall resistance. The downside of doing this, of course, is you have to pay attention that you don't block precious routing tracks with unnecessary via pillars. Another strategy that's commonly used is to use continuous OD for better matching and performance and matching. So the idea here is that when you have a short active area, you get a lot of variation in mobility and therefore stress and therefore mobility. However, if you build a plateau, pay a tax of dummy gates at each end, basically the mobility starts to saturate. And therefore, if you basically use devices on this plateau, you're much better in terms of matching. Okay. Yeah. Another note here, avoid resistors as much as you can, because resistors are getting more and more expensive in each node. It's becoming more popular to use resistorless topologies and having the overhead of pretty cheap logic and control logic to basically calibrate. If you can avoid bipolars and diodes, if at all possible, that would be good. It's not easy to do. You know, we're already introducing all sorts of different plethora of circuit tricks to overcome non-idealities and say a conventional bipolar-based band gap reference and thermal sensor. So there's a lot of challenges to try to eliminate diodes. There are alternatives being explored, but you know, the problem, for instance, with thermal sensors is accuracy and simple single temperature calibration. Obviously, with the high density of heat, we need to do things to mitigate self-heating, all sorts of, you know, the usual reliability concerns. And so the strategy is pretty obvious. We really don't have a simple solution to reduce the amount of heat being generated, but can we sink the heat away effectively? And so these are just some strategies here, how you would have dummy devices to spread the heat around, funnel the heat to, for instance, well taps, to the well, to the overlying metallization, and so forth. Now, there are things that can be done also. You know, we talked about using speculative models, how to deal with target-based uncertainty. So the process is going to be much more immature in each new node now than, say, 5-10 years ago, simply because there are more mass and longer fab cycle times associated with getting a wafer from start to finish, which means fewer cycles of silicon learning. With that said, the fab is actively scrambling to basically still do some process development, tweaking, etc., well after tape out. And the usual areas are in the transistors as well as the middle end of line. These are typically the most aggressive area, most aggressively pushed for area reduction, which means that the models have unstable parameters such as the VT, mobility, layout dependent effects, and so forth. And so, you know, with all this said, it is important to incorporate more design margin, but you don't want to overdo it. So one way to alleviate some of these or mitigate some of these uncertainties and to basically have faster design closure is to use template-based cells for instance, for analog mixed signal, used analog cells, for instance, that are essentially analogous to standard cells for digital gates. Okay, so the idea here is that you have layout considerations incorporated in these supersized P cells that have process-friendly layout guidelines. You're trying to anticipate density concerns that you will have as you start to assemble more and more of these blocks at a higher level, using short channels wherever you can, predefined routing tracks, and if you can somehow back annotate some of the include some of the middle end of line and the lower back end of line to make things easier to assemble, that would be great. You can have smarter schematics to reduce the simulation gap. For instance, you can anticipate that if you're going to have, for instance, devices in a continuous OD placement, you can override the SA and SB parameters to minimize that gap and have more middle end of back end aligned parasitics back annotated into the schematics. Okay, with that said, I'd like to wrap up with a short look at what's ahead. In terms of squeezing out what's left in FinFETs, suffice to say, every generation of the last 4 has been, very, very tough. Okay, there really is no low-hanging fruit in each new node, and what I've certainly seen is that the level of process innovation and complexity required for a very small incremental gain is actually pretty intense. To get something as seemingly trivial as a 5% ring oscillator frequency boost is actually a super big deal. Okay, and in terms of the areas of development, pretty much no stone is left unturned. Every aspect of how to get more performance out of the transistor in smaller area is being squeezed to the very last bit, but this all has to be carefully balanced with the increased complexity and associated cost. This takes us now to the next part of our journey, which, when will it happen? The problem with FinFET, of course, is that we have poor short channel control with further L-gate scaling. And that's largely because, the FinFET has poor channel control, short channel control at the very bottom of the fin where the gate is not wrapped around the channel. And so as we are looking for alternatives, what we need to make sure is that the next device architecture we migrate towards not only has better short channel control as we try to scale the gate length, but also we need to make sure that the effective width per die area also improves so that we can have a higher density of transistor current per unit area. Okay, and so the most promising are the nanowires and the nanosheets. Okay, and so we have basically a stack of multiple of these nanosheets here, for instance. Nanowire is kind of the limit when you have very, very narrow nanosheets. They are promising. We pretty much have to stack multiple devices, multiple sheets or multiple wires to even make it worthwhile. Otherwise, FinFET's going to give you better device width density. Now, the nanowires, by virtue of the gate wrapped around in much closer proximity to every point in the nanowire, is going to give you better short channel effects. However, you're going to get better area scaling. And so, just from a simple crystal ball opinion here, I do not expect nanowires to see light of day. We will probably migrate directly to nanosheets, even because of the effective width scaling proposition. Okay, so looking at how nanosheets would vary, what's it like compared to FinFET? From a designer's perspective, it's really not that different. If you've got, for instance, say a couple of FinFETs here, you're migrating to a nanosheet. Well, as you migrate to nanosheet, now you have more control over the width of the nanosheet. Okay, which brings us back more to the flexibility of what we had with planar transistors. Looking at the cross sections a little bit more complex, you can see in the Y cut, you see the stack of, say, the different nanosheets here. I'm showing 4 in this example here. In the X direction, we've got our source drain. We've got our, our gates in between, and also, the nanosheet current would be flowing along in the green, the active area here. Now, there are some subtleties here to highlight. number one, the current will flow mostly along the 100 direction again, like a planar days. Okay, it's just that we have now both top and bottom side current flow, and so this is going to mean that our electrons are going to be happier compared to our holes, meaning that our beta ratios are going to move back away from unity, as it was the case for FinFETs. You do need to have build these so-called inner spacers, so to speak. Otherwise, you have very, very intense high capacitance coupling from the gate to the source drain regions, which would make the capacitance story of a nanosheet dead on arrival without the inner spacers. Also, another key thing is because we do have a parasitic planar device here, which, as we know, has really crappy short channel effects, because that's the whole point of you migrating to FinFET. We need to basically have very, very heavy anti-punch through implants in the region here in order to turn off these parasitic devices beneath the nanosheets. And the other thing also to keep in mind is that for current to travel from the gate, for the source drain contacts down to the very bottom nanosheet, the series resistance of the source drain is very, very high. And so there is a limit to how much we can keep stacking these devices. Looking further, this is where, we're running out of steam with silicon scaling, geometric scaling of the channels. And this largely because when you scale the silicon channel thickness less and less and less, the surface scattering causes the mobility of silicon to basically plummet very, very quickly. And so this has given rise to a lot of intense R&D into what's referred to as atomically smooth 2D materials, such as molybdenum disulfide, tungsten disulfide, etc. These are referred to as transition metal dichalcogenides because they consist of one atom of a transition metal and two atoms of a chalcogen column in the periodic table, and also, of course, carbon nanotubes. Okay, and so here these materials fundamentally have much, much higher mobilities as you scale down the channel thickness. So with that said, I'd like to conclude. Thanks very much for your time. So with that said, hopefully, you've been convinced that, as we're moving through, with the technology scaling, despite all the challenges, okay, at least moving into the 5 and even 3 nanometer, Moore's law is still very well and alive. It's not even sick. A very nice quote given by Professor Philip Wong from Stanford. And even, as monolithic integration starts to be limited. I mean, Moore's original paper actually prophesized having heterogeneous integration as well. Okay, now hopefully you're convinced that all the area scaling we're seeing now is predominantly driven by device innovation and a lot of design technology co-optimization, much less so by actual feature size reduction. If you're looking at FinFET area scaling, it's clearly tailored towards logic and memory, where typically more than 90% of the area of the die is focused, and not so much on classic analog. What that means is that if we're going to build analog mixed signal systems, we're going to need a lot more, sweat a lot more to get that implemented for very, very little improvement in performance. But that's just the nature of the beast. And hopefully we're all convinced that understanding and exploiting the technology is really, really key, not just to get the value out of the process, but also to do it as efficiently, time-wise as possible. Okay. With that said, I'd like to thank my friends and former colleagues at Qualcomm and TSMC who are instrumental in putting together some of this, providing some of the content of this material. And there are a list of references here that welcome you to look at. And at this point, I'd like to take some questions. There's still time. Thank you for your attention.
Okay, there is time for a question. Thank you, Alvin, for this very nice presentation. Yeah, we do have a questions from the audience here. Let's start with one that has to do with analog cells. Analog designers here in the audience.
Yeah.
The question is, the move to using template-based analog cells, does it bring a hope for analog design automation at these advanced corners?
Yes, it does. In fact, so I did not pay to ask that question, get that question asked, but absolutely. I mean, basically, if you have constrained blocks or constrained cells, right? It's no different than standard cells, right? And so, having, for instance, like predefined ports for instance, automated place and route. There is a lot of research that has gone into this, although nothing definitive from the key vendors yet, but certainly a lot of active research done. For instance, the notable one by Professor Elad Alon from Berkeley, doing all the work related to the analog generators. Okay, so for instance, having constrained template cells that the analog generators would operate on would be the very, very obvious thing to try. And so, yes, that is the direction analog designers should head towards. In fact, actually, because as you can see, the process is so sensitive to all these micro-loading effects and so forth, you can see that the freedom that designers have to lay stuff out is getting less and less and less. And so, at the end of the day, ultimately, I think we're going to be left at some point to essentially lay out cells for analog application that very much look like digital standard cells. So that's a very good question.
Yeah. This is very complicated nodes. There are two questions here in both. Thank you very much for your very nice presentation in this course and this excellent lecture.
My pleasure.
They have two questions that are related to the flicker noise. You had some data on the increment of flicker noise. So you mentioned the increase in the flicker noise. Does it imply a tendency to use low IF RF receivers instead of direct conversion RF receivers? Question comes from Sandro Ferreira. Professor Sandro is, of course, working on RF CMOS, and he's asking if the tendency would be to low IF instead of direct.
Oh, low IF instead of zero IF, you mean?
Right, yeah.
Yeah, I'm sorry, Professor, I'm not qualified to answer that question.
Yeah, well, RF transceivers are a very complicated subject.
Yeah.
And indeed, but there is one that's more device related here. It comes from someone in the audience that says that from the flicker noise table that you reported, it seems that the PMOS has much more flicker noise. Yes. This seems opposite to the long channel behavior that he's used, the speaker, not the speaker, but the people asking is used to. So is there a physical reason for that? Is that a physical reason for that in FinFET, the PMOS has more flicker noise?
There are. It's related to a host of different reasons. I can't tell you exactly the relative importance of all these reasons, but one, for instance, it's related to the fact that we are having a 110 instead of 100 sidewall of the FinFET, where most, basically 90-95% of the channel width is, right? So we've got basically the channel has a different normal, and as a result, different atomic density, different trap density. So that's one aspect of it. Okay. Another aspect of it also is related to the impact of stress, which I'm not super familiar with all the subtleties, but stress has a different impact on the mobility and so forth. The other thing also is you've got the HighK metal gate. The interface is not going to be the same quality as before, and you've got different impact on the dielectric will be different whether you have an NMOS or a PMOS, and that also has an impact. And lastly, as TSMC announced, although it doesn't share any details as to the material that's used in the PMOS, TSMC has announced in last year's IDM that it has migrated to a different device material for building its PMOS transistors. And so And so, you know, when you got different materials, you're going to have different trapping, detrapping properties, and therefore differences in 1/f characteristics. So I'm not sure if that provides some light, but yeah.
I have one question on my own. You know, in this FinFET nodes, like say the 4th generation, you mentioned that the threshold control for having different VT transistors, you can play with the metal gate composition and metal gate grain orientation, or else you could play with the composition of the dipole in the HighK perovskite. You know, that's correct. What is the compounding those two levers in the process? How many thresholds can you still you know, control reasonably? And do they prefer the metal grain, the metal gate grain orientation effect, or the HighK dipole effect to, let's say, have low VT and mid and regular VT?
That's an excellent question. So, typically in an advanced node, it is you can quite often get as many as 4 VT flavors per transistor type. So 4 core oxide NMOS, 4 VT for PMOS, and then you've got typically 1 flavor for your I/O device, one NMOS and 1 PMOS for the thick oxide. Okay. Having said that, you know, the VT flavors are all offered, right? But you know, the foundries will not tell you exactly how they sequence, you know, how they're using the different gate work functions and also the dipoles to get the different VTs. But some VTs are more prioritized than others. Having said that, so typically it's the higher performance ones that matter more. You know, it comes down to the fab being able to build the various VTs, but then the model accuracy of some will be suspect compared to some others. Okay. With that said, there is an increasing push to move more and more towards the dipole-based VT control, which sometimes is referred to as a volumeless approach, because the problem with using different materials, metal gate materials, right, to adjust the VT work function, or sorry, the work function of a gate, is that you'll be dialing the material, you'll be dialing the thicknesses of the materials and so forth, and that takes up space. So you can imagine that this is a tremendous problem as you're moving, for instance, towards nanosheets. Okay, so in a FinFET process, the gap between your fins, you know, you've got somewhere in the order of typically about 20 nanometers space between the fins to you know, to deposit all these different layers of the HighK and the metal gate. But then in a nanosheet, right, we're talking about spaces in the order of maybe 10 nanometers between the sheets. Okay, and so you can imagine that if you use
the vertical direction, in the vertical direction,
exactly, okay, between the sheets, yeah, okay, between the sheets, we're talking, if I may go to the slide here, we're talking about 10 nanometer space between here. Okay, can you see my mouse? Right. Okay.
Yeah, the mouse
in
is contrast,
coming up. Yes. That's right. In contrast, for the FinFET, the space between the fins is about double that.
20.
Okay.
But
so what that means?
20 when you use a quadruple patterning, you know, sidewall, right?
You're using that for sure. Yeah, definitely. If you want to get to the more aggressive fin pitches, it would be self-line quadrature patterning. That's right. So you're doing spacer-based patterning twice. That's right.
Yeah, the process is very complex, and our audience here is appreciating very much that you're sharing this complexity with us. You know, it's very, you know, also the prospect of moving directly to nanosheets. I think that there are compelling reasons that you pointed that nanosheets will be a competitive, let's say, device architecture for the next generation, and then you know, beyond, you know, FinFET.
It remains to be seen. I think that the problem that the foundries face is how many customers will actually be able to afford building in these nanosheet nodes.
Yeah. Okay.
Right.
Yeah. The cost is another very important issue. I have one question here from Pedro Toledo. He's in Italy, and he's a PhD student. He does analog design, and he thanks you very much for a very nice talk. And he has worked with analog designs in which he takes profit of the zero temperature coefficient current when you go from, let's say, from diffusion, sub-threshold to super threshold. You have a zero temperature coefficient point in bulk transistors. So do you have any comments about the ID versus VG, that characteristics has for different temperatures? Does it exhibit a zero temperature coefficient VGS or in FinFETs in those?
Okay, so if I understand this correctly, basically the question is, thank you for the question, by the way, and thanks for your time to listen to this. So you're talking about basically finessing how gate overdrive and VTs are essentially changing and canceling each other, so to speak, such that you have no change in VGS to achieve the same current, right?
Yeah, well, zero temperature coefficient. It is in the bulk transistors is when you go from low VG and you are, let's say, mid-level inversion. So and then it goes to strong inversion. And there's a transition point here in VG in the x-axis where the log of ID has a zero temperature coefficient around, in some technologies like 0.13 and 0.18 micron is like around 0.8, 0.7, 0.8, 0.9 volt. And his thesis here, Pedro has exploited this property, but he never worked with FinFET. He's curious if that effect is present there.
Yep. So in terms of the mobility changing with temperature, that's still the same. I mean, it's still monotonically decreasing with temperature, right? In the temperature range of interest. In terms of VT, now granted, VT change versus temperature is now is going to be dependent on other properties now, right? It's going to be largely dependent on essentially the work function, a lot more so than say, silicon becoming intrinsic as you increase in temperature. But the VT dependence on temperature is still also monotonically decreasing with increasing temperature. So, all I'm saying is those the polarities of the temperature dependencies of VT and mobility has not really changed in an appreciable way in going to these FinFET nodes. So long story short, I think yes, you can play these tricks if to finesse that in a FinFET node. I don't see that changing.
So now the very last question has to do with academics who use predictive modeling, because they, most students in these regions do not have access to commercial PDKs for FinFETs, first or second or third or fourth generation FinFETs. So most of them resort to using the Arizona State University ASAP predictive FinFET educational PDKs. So how do you rate those, let's say, public domain FinFET predictive models from Arizona State for educational? I think the question is, how do you rate them? But I myself, I praise them for doing that for the community. I do not rate them. I praise them to do that because it's always predictive. It's not really committed to mimic any commercial foundries results. But
yeah, I'm sorry. I'm quite ignorant on that because this is not a space where I have any direct experience working with these predictive models. I mean, what I can say about these models, they're very complex, right? And actually, I've lost track of a lot of this, but I mean, they're all surface potential based.
Yeah, the reason being that in this part of the world here, where university students don't have access to the commercial PDKs, they go to the Arizona State University site for ASAP. They download the SPICE models, they design rules. There are, let's say, guess rules, educated guess rules, trying to mimic what's going on in the real world, in commercial arena, and many students use those PDKs. So I thank you all of that for coming and addressing the questions to Alvin. It's been a long journey. Thanks a lot for your very nice presentation, very nice course. I know you delivered this mini course in 90 minutes, and you made all the effort to cover all the material, very, very depth material, very, go into depth. You know, I leave the floor for you to say, you know, the last words to our audience, and then we close the session. And
yeah,
in January,
sure.
we go again for the next. Late January, we'll announce the new webinars that we have. So the floor is yours, Alvin, for your last words.
Thank you. So, you know, I just want to say obrigado. I mean, thank you very much for the opportunity to do this. I think, you know, Sergio, you and your team have done a fantastic job for, you know, what you've done in your chapter. And, you know, it sounds like done even more outstanding things, even, you know, above and beyond, you know, stuff you've already been doing since I last visited your university, I guess 7 years ago. So,
long time.
you know, I just want to say that, you know, thank you. Keep up the great work, and you know, I just want to say, you know, I'm pretty accessible. So, if folks would like to reach out and ask me some questions, my email is simply, you know, alvin.loke@ieee.org, and you know, feel free to reach out to me if you have some questions. And you know, I want to wish everyone continue to stay well, and you know, we'll get through this together, and you know, hopefully sooner than later, we will be seeing each other in person.
Good. Again,
happy holidays. Yeah.
Thanks a lot. Happy holidays to everyone here in Cyberland. You know, we close the